The Agile Pipeline, building, testing, and delivering software with CI/CD. 1. The software delivery maze. Why we need a better way. 1.1. The pressure cooker of modern software. In the blink of an eye, software has gone from a specialized tool for experts to the invisible engine powering nearly every facet of our lives. From ordering groceries to connecting with loved ones across continents, from managing global supply chains to navigating city streets, software is everywhere. This pervasive influence has placed an immense pressure on businesses. Innovate faster, deliver more features, and maintain impeccable quality, all while staying ahead of relentless competition. Gone are the days when a company could afford to release major software updates once a year or even quarterly. Market demands, customer expectations, and technological advancements now require a continuous flow of improvements. Businesses that can adapt quickly, experiment freely, and provide immediate value to their users are the ones that thrive. Those that falter, stuck in sluggish delivery cycles, risk becoming digital dinosaurs, unable to keep pace with the agile predators of the modern market. But this speed and quality come at a cost, often hidden. For many organizations, the process of turning an idea into working software that reaches users is still a perilous journey. It's a maze fraught with pitfalls, delays, unexpected errors, communication breakdowns, and the constant threat of a critical bug slipping through the cracks. These challenges don't just impact technical teams, they translate directly into lost revenue, diminished customer trust, and a demoralized workforce. 1.2. The traditional gauntlet. Waterfall and its woes. For decades, the dominant approach to software development was often likened to a cascade, the waterfall model. Imagine a project where each phase flows strictly downwards, like water cascading from one level to the next. You define all requirements up front, then design the entire system, then implement it, then test it, and finally deploy it. There's no going back up the waterfall once you've descended. While seemingly logical and organized, this linear approach quickly revealed its shortcomings in the real world of software. Long delays before feedback. With all requirements defined at the start and testing happening only at the very end, stakeholders often wouldn't see working software until months, sometimes even a year, after the project began. By then, market needs might have shifted, or initial assumptions might prove incorrect, leading to costly reworks. Big bang releases. Because everything was built and tested in one massive cycle, releasing a new version of the software became a monumental, high-risk event. Imagine launching a rocket without a detailed pre-flight checklist. The team would collectively hold its breath, hoping against hope that nothing critical would break. These Big Bang deployments were often scheduled for off-peak hours, involving late nights, high stress, and the very real possibility of widespread system outages. Siloed teams blame games. In the waterfall model, developers would often throw their completed code over the wall to the quality assurance (QA) team, who would then throw accepted code over another wall to the operations (Ops) team for deployment. Each team had its own goals, tools, and often its own set of frustrations. When problems arose, which they invariably did, it was easy for a developer to say, "It worked on my machine," or for Ops to retort, "This code broke our servers." Communication was fragmented, and blame was often abundant. Difficulty responding to change. The waterfall model inherently resists change. A shift in requirements midway through development could derail an entire project, requiring costly replanning and extensive delays. In today's dynamic markets, this rigidity is a death sentence. 1.3. The pain points. What goes wrong in the maze? These traditional approaches turn software delivery into a relentless gauntlet of pain points, manual handoffs, and bottlenecks. Every time a human element is required to pass something along code, documents, test results, it introduces delays and the potential for errors. These bottlenecks are like traffic jams in the software delivery highway, slowing everything down. "It worked on my machine" syndrome. This legendary developer's lament highlights a core integration problem. Code works perfectly in a developer's isolated environment, but when combined with others' code or deployed to a new server, it breaks. This leads to frustrating detective work and hours lost tracking down environmental discrepancies. Bugs found too late. The longer a bug remains undetected, the more expensive it is to fix. A bug caught during development might take minutes to resolve. That same bug, discovered by a customer in production, could cost thousands in incident response, reputational damage, and lost business, not to mention the emotional toll on the team. Deployment anxiety. For many teams, release night is a terrifying ordeal. It involves meticulous checklists, often manual steps, crossing fingers, and hoping the complex deployment script doesn't introduce any new problems. This stress is unsustainable and a significant morale killer. Burnout and frustration. When teams are constantly fighting fires, dealing with repetitive manual tasks, and enduring high-stress releases, morale plummets. Talented engineers become disillusioned, and the constant pressure often leads to burnout and high employee turnover. Consider Sarah's team at a promising tech startup. They prided themselves on delivering monthly releases. However, each month became a chaotic sprint. The last 2 weeks of every cycle were dominated by grueling manual testing, fixing integration issues, and then the inevitable all-nighters for deployment. Bugs were often discovered in the final hours, leading to cascading delays and hotfixes. Management celebrated the on-time release, oblivious to the exhaustion and dread that permeated the team. Sarah often wondered there had to be a better way, a way to deliver value that wasn't just fast, but also calm, predictable, and sustainable. 1.4 A glimmer of hope. What if it could be better? What if that monthly struggle could be transformed into daily, even hourly, occurrences of smooth, confident deployments? What if software could be delivered not just quickly, but with inherent quality, where bugs are caught moments after they're introduced, not weeks or months later? The good news is, it can be. The answer lies in transforming the chaotic maze into a streamlined, automated, and continuous flow, what is often referred to as a pipeline. This pipeline acts like a well-oiled assembly line for software, where every step from writing code to releasing it is automated, tested, and optimized for speed and reliability. This is the promise of continuous integration, CI, and continuous delivery, CD. It's a set of principles and practices that leverage automation to eliminate the friction points in the software delivery process, allowing teams to deliver high-quality software with unprecedented speed and confidence. 1.5 What you'll learn in this book. This book is your guide through the intricacies of CI/CD, transforming the daunting maze into a clear path. We will explore how CI/CD solves the problems of traditional software development, fostering faster feedback, higher quality, reduced risk, and improved collaboration. The foundational philosophies of Agile and DevOps that pave the way for CI/CD. The core components of continuous integration, CI, from version control and automated testing to the execution of your first build pipeline. How continuous delivery, CD, extends CI, ensuring your software is always ready for release, bridging the gap to production. The brave new world of continuous deployment, where code progresses directly to users and the strategies to achieve it safely. The crucial role of monitoring and feedback in completing the delivery loop, ensuring you learn from every release. The often overlooked but essential human element. The cultural shifts, collaboration practices, and change management required for successful CI/CD adoption. A landscape tour of the tools and emerging trends that support CI/CD practices. Finally, a practical roadmap to help you embark on your own CI/CD journey, whether you're starting from scratch or looking to optimize existing processes. Understand that CI/CD is not merely about adopting a new set of tools, it's a fundamental shift in mindset. It's about building quality in from day one, embracing automation as a partner, and fostering a culture of continuous improvement and shared responsibility. By the end of this book, you will have a clear understanding of why CI/CD is indispensable in today's software landscape, and how you can harness its power to build better software, faster, and with more confidence. Chapter Summary. Traditional software development, often characterized by the waterfall model, struggles to meet the demands of modern markets due to long feedback cycles, high-risk, big bang, releases, and siloed team structures. This leads to common pain points like manual bottlenecks, frustrating integration issues, late-stage bug discoveries, and deployment anxiety, ultimately impacting business agility and team morale. However, a transformative solution exists in continuous integration, CI, and continuous delivery, CD. These practices automate the software delivery pipeline, promising a future of faster, higher quality, and more reliable software releases. This book will serve as your comprehensive guide to understanding and implementing CI/CD, emphasizing its principles, benefits, and the cultural shifts necessary for success. 2. Introduction to Agile and DevOps, the foundation of modern delivery. To truly grasp the power and purpose of continuous integration and delivery, we first need to understand the fertile ground from which these practices sprang. CI/CD isn't a standalone innovation. It's a vital component of two broader, interconnected philosophies that have reshaped the world of software development: Agile and DevOps. Think of them as the philosophical and operational parents of CI/CD, providing the why and setting the stage for the how. 2.1. The Agile Revolution. Responding to change. For decades, the waterfall approach, with its rigid, linear progression, dominated software development. But by the late 1990s, cracks in this model became increasingly apparent. Businesses were struggling to adapt to rapidly changing markets and customer needs. Long development cycles meant that by the time software was delivered, it might already be obsolete. In response to these predicaments, a small group of software developers and thinkers met in February 2001 in Utah. They weren't looking to create a new methodology, but rather to find common ground on practices that allowed teams to deliver software more quickly and effectively. The outcome of their discussions was the Agile Manifesto, a deceptively simple document centered around 4 core values: individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, responding to change over following a plan. These values were supported by 12 principles, advocating for practices like frequent delivery of working software, weeks rather than months, close daily collaboration between business people and developers, self-organizing teams, and continuous attention to technical excellence. From these principles emerged various Agile methodologies like Scrum, Kanban, and Extreme Programming XP. While each has its nuances, their shared emphasis fundamentally shifted the paradigm: iterative development. Instead of one long cycle, work is broken into short, repeating cycles, often called sprints or iterations, typically lasting 1 to 4 weeks. Each cycle aims to deliver a small, working increment of software. Rapid feedback loops. By delivering working software frequently, teams can gather immediate feedback from users and stakeholders. This feedback is then used to refine future iterations, enabling teams to pivot quickly and ensure they're building the right product. Cross-functional teams. Agile encourages teams that possess all the necessary skills, development, testing, design, to complete a piece of work, minimizing handoffs and fostering shared ownership. Emphasis on working software. The ultimate measure of progress is working software, not reams of documentation or perfectly followed plans. Continuous integration, in particular, found a natural home within the Agile movement. Rapid, iterative development meant that developers were building and merging code more frequently than ever before. This necessitated robust, automated checks to prevent integration chaos. CI became one of the technical cornerstones, enabling the Agile ideals of continuous delivery of working software and responding to change. 2.2. Bridging the divide. The rise of DevOps. While Agile dramatically improved the development side of software creation, a new problem began to emerge. Development teams, empowered by Agile practices, were able to build features faster than ever. However, getting these features into production often remained a slow, cumbersome, and conflict-ridden process. The traditional divide between development, who wanted to move fast and change things, and operations, who wanted stability and reliability, deepened. This became known as the wall of confusion, or the dev versus ops problem. This friction was epitomized by incidents like the 2009 Velocity Conference, where Flickr famously presented their 10+ deploys per day presentation, highlighting the stark contrast to most organizations struggling with quarterly or even yearly releases. This sparked a conversation about how to bridge the gap. The term DevOps itself gained traction around 2009, popularized by figures like Patrick Debois and his series of DevOps Days conferences. It wasn't about creating a new role or a new team. Rather, it was a cultural movement aimed at fostering better collaboration and communication between development and operations teams, extending the agile principles of integration and automation across the entire software delivery lifecycle. At its core, DevOps focuses on 5 key pillars, often remembered with the acronym CALMS. Culture, perhaps the most crucial pillar. DevOps fosters a culture of shared responsibility, collaboration, trust, psychological safety, and empathy between teams. It promotes a blameless approach to failures, focusing on learning and improving processes rather than finding scapegoats. Automation. Automate everything that can be automated, from building and testing to infrastructure provisioning and deployment. This reduces manual errors, increases speed, and frees up human creativity for more complex problems. Lean. Inspired by lean manufacturing principles, this pillar focuses on maximizing customer value while minimizing waste. It advocates for smaller batch sizes, reducing work in progress and continuous flow. Measurement. You can't improve what you don't measure. DevOps teams use metrics to understand performance, identify bottlenecks, and drive continuous improvement. This includes tracking deployment frequency, lead time for changes, mean time to recovery (MTTR), and change failure rate. Sharing. Knowledge, tools, and processes are shared openly across teams. This fosters cross-pollination of ideas and builds collective expertise. A simple analogy to understand DevOps is of a racing pit crew. In traditional software, the mechanics, developers build a fast car, but then there's a separate team responsible for getting it onto the track and keeping it running operations. In the DevOps model, everyone on the pit crew works together, sharing knowledge, constantly optimizing their process, and understanding each other's roles to ensure the car, the software, is always performing optimally during the race in production. The DevOps philosophy is often visualized as an infinite loop, representing the continuous flow of activities. Plan right arrow code, right arrow build, right arrow test, right arrow release, right arrow deploy, right arrow operate, right arrow monitor. Back to plan. This DevOps loop emphasizes that software delivery is not a linear process, but a continuous cycle of creation, delivery, and feedback, with learning and improvement baked into every stage. 2.3 CI/CD as a cornerstone of DevOps. It should be clear now how continuous integration and delivery slot perfectly into this broader picture. CI/CD isn't just a set of technical practices, it's the technical backbone that enables Agile and DevOps to truly flourish. Enabling Agile principles. CI provides the rapid feedback loops and continuous integration necessary for Agile teams to deliver working software frequently. CD ensures that this working software is consistently in a deployable state, allowing for true responding to change rather than being bogged down by deployment anxiety. Embodying DevOps pillars. Automation. CI/CD is automation. It automates the builds, tests, and deployments that were once manual, tedious, and error-prone. Lean. By automating the pipeline and reducing batch sizes, smaller, more frequent changes, CI/CD eliminates waste and improves the flow of value. Measurement. Feedback from the CI/CD pipeline, pass-fail rates, build times, test coverage, provides crucial metrics for continuous improvement. Culture and sharing. The transparency of a CI/CD pipeline, where everyone can see the status of builds and deployments, fosters shared responsibility and collaboration. It breaks down the DevOps wall by giving both teams a shared process and shared visibility into the software's journey. Without robust CI/CD practices, an organization can espouse Agile and DevOps principles, but it will struggle to realize their full potential. You can't genuinely do DevOps if your deployments are still manual, painful, and infrequent. CI/CD is the engine that drives the continuous flow that both Agile and DevOps strive for. 2.4 Mindset shift. From project to product, from silos to flow. Ultimately, the adoption of Agile, DevOps, and by extension, CI/CD, necessitates a significant mindset shift. It moves away from viewing software development as a series of isolated projects with definitive start and end dates, towards a product-centric view where software is continuously evolved and delivered to provide ongoing value to users. It means moving from silos to collaboration, breaking down walls between development, operations, and quality assurance. Fixing to preventing, catching issues early through automation rather than fixing them late. Fear to confidence, making releases routine and boring rather than scary and stressful. Output to outcome, focusing on delivering value and impact, not just completing tasks. This shift isn't just about tools or methodologies. It requires leadership buy-in, continuous learning, and a willingness to embrace change and foster an environment where experimentation and rapid feedback thrive. The chapters that follow will delve into the technical mechanisms and practices that make up CI/CD, providing the practical steps to enable this powerful transformation. But remember, the technical details are only powerful when built upon this foundation of Agile principles and the collaborative, automated, and continuous spirit of DevOps. Chapter Summary: Continuous Integration and Delivery, CI/CD, is fundamentally rooted in the philosophies of Agile and DevOps. Agile revolutionized development by emphasizing iterative work, rapid feedback, and responsiveness to change. However, it exposed a bottleneck between development and operations. DevOps emerged to bridge this gap, fostering a culture of collaboration, automation, lean practices, measurement, and knowledge sharing across the entire software delivery lifecycle. CI/CD perfectly embodies these principles by automating the software pipeline from code commit to deployment, turning a traditionally painful process into a continuous, high-speed flow. Understanding this foundational context is crucial for appreciating the why behind CI/CD's powerful capabilities and its role in modern software practices. 3. Continuous integration. Building quality in continuously. Imagine a symphony orchestra where each musician practices their part in isolation for weeks. And then, on the day of the performance, they all try to play together for the very first time. The result would be chaos, a cacophony of disjointed sounds. Instead, musicians rehearse frequently, integrating their parts, listening to each other, and making adjustments on the fly. This constant integration and feedback is what allows them to create beautiful, synchronized music. In software development, your code is like a musician's individual part, and the entire application is the symphony. If every developer works in isolation on their branch for days or weeks, then tries to merge their changes all at once, you're setting yourself up for an integration nightmare. Welcome to the problem Continuous Integration, CI solves. 3.1 Introduction. What is continuous integration? At its heart, continuous integration, CI, is a software development practice where developers frequently integrate their code changes into a shared main branch, often called the mainline or trunk. Crucially, each integration is immediately verified by an automated build and a suite of automated tests. The primary goal is to detect integration errors as quickly as possible, ideally within minutes of them being introduced. The concept was pioneered by Grady Booch in the 1990s and became a core practice of extreme programming (XP), a lightweight agile methodology. It directly counters the problem of integration hell, where merging large code bases after long periods of individual work becomes a painful and lengthy process, often introducing new bugs. Instead of waiting for days or weeks to integrate, CI encourages developers to integrate their code multiple times a day. Think about it. If you discover a problem after 100 changes made by 5 different people, pinpointing the source of the error is like finding a needle in a haystack. But if you discover it after just 3 small changes made by one person, the fix is usually quick and straightforward. 3.2 The core principles of CI. Implementing CI effectively isn't just about using a tool. It requires adhering to several key principles. Maintain a single source repository for the project. All code, configurations, and build scripts live in one central, version-controlled place. This ensures everyone is working from the latest and correct version of the codebase. We'll dive deeper into version control in Chapter 4. Automate the build. Compiling, packaging, running static code analysis, and any other steps required to produce a runnable application must be fully automated. No manual command line steps or specific environment setups should be needed. This ensures consistency and reproducibility. Automate the test. A comprehensive suite of automated tests, primarily unit and integration tests, should be part of the build process. If any test fails, the build fails. This is your immediate quality gate. We'll explore automated testing in detail in Chapter 5. Every commit triggers a build. Whenever a developer commits code to the shared repository, the CI system should automatically detect this change and trigger a new build and test run. This provides immediate feedback on the impact of each code change. Fix broken builds immediately. This is perhaps the most critical principle. If a build fails, red light, everyone on the team stops what they are doing to help fix it. This stop-the-line mentality, borrowed from lean manufacturing, ensures that problems are addressed before they can propagate and become larger, more complex issues. Ignoring a broken build sets a dangerous precedent and undermines the value of CI. The build should be fast. To support frequent integration and immediate feedback, the automated build and test process should complete quickly, ideally within minutes. If it takes hours, developers will integrate less frequently, defeating the purpose of CI. Tests are self-testing. The tests themselves must be reliable and deterministic. A flaky test, one that sometimes passes and sometimes fails without code changes, erodes trust in the system and leads to builds being ignored. Make build status visible to everyone. The status of the latest build, green for success, red for failure, should be prominently displayed, perhaps on a large monitor in the team area or a dashboard. This transparency promotes accountability and informs decisions. Automate deployment to an integration environment. While the focus of CI is build and test, ideally the process also pushes the successfully built artifact to a shared integration environment for further testing or demonstration. 3.3 The CI process in action, high level. Let's illustrate the typical flow of continuous integration. Developer action. A developer finishes writing a small piece of code or a new feature. Commit code. They commit their changes to the shared version control repository, e.g. Git. CI server trigger. The CI server, e.g. Jenkins, GitLab CI, GitHub Actions, automatically detects the new commit. Fetch and build. The CI server pulls the latest code from the repository and runs the automated build process, compiling the code and resolving dependencies. Run automated tests. Immediately after a successful build, the CI server executes the automated test suite, unit tests, basic integration tests. Report status. The CI server reports the results of the build and tests. Success, green build. If everything passes, the build is green, and the developer and team receives a notification of success. The new code is integrated and ready for the next step. Failure, red build. If the build fails or any tests fail, the build turns red. An immediate notification is sent to the developer who committed the change and often to the entire team. Fix immediately. The responsible developer, with the team's support if needed, drops what they are doing to fix the issue. This often involves reverting the problematic change, fixing the bug, or correcting the failing test. Repeat. Once fixed, the process starts again with a new commit, ensuring the main branch is always stable and working. This rapid feedback loop is the essence of CI. It moves quality control from the end of the development cycle to a continuous, integrated part of the process. 3.4 Benefits of continuous integration. The advantages of adopting CI are profound and directly address many of the pain points discussed in Chapter 1. Early bug detection and resolution, the most significant benefit. By catching integration issues and bugs within minutes of their introduction, the cost and effort of fixing them are dramatically reduced. It's like finding a small leak in a pipe before it floods the entire house. Reduced integration headaches. Say goodbye to merge hell. Frequent integration means smaller merges, fewer conflicts, and a drastically lower chance of code breaking when combined. Constant code quality, automated tests, and static analysis become integral to the definition of done. This enforces coding standards and maintains a higher baseline quality for the entire codebase. Increased confidence. developers gain confidence that their code changes aren't breaking existing functionality. This psychological safety encourages them to commit frequently and make necessary refactorings. Improved team collaboration and communication. CI promotes shared ownership and encourages developers to communicate more frequently about their changes. The immediate visibility of build status, green-red, fosters a sense of collective responsibility. Always a deployable artifact, or nearly so. A successful CI pipeline consistently produces an artifact, a compiled and tested version of your application that is ready to be delivered. This is a critical prerequisite for continuous delivery. Faster development cycles. Although it might seem counterintuitive to stop the line, the time saved by preventing integration nightmares and late-stage bug fixes far outweighs the brief pauses to address red builds. Overall development velocity increases. 3.5 Common misconceptions and pitfalls. While the benefits are clear, there are common misunderstandings and pitfalls to avoid when implementing CI. We just run builds automatically overnight, isn't that CI? No. If your builds are not triggered by every commit and if feedback isn't immediate, you're missing the core principles. Daily or weekly builds are batch processing, not continuous integration. We don't have time for automated tests. This is a false economy. A CI pipeline without comprehensive, reliable automated tests is a dangerous illusion. It might build code, but it won't tell you if the code actually works or if it broke something else. It's like having an assembly line that puts all the parts together but never checks if the final product functions. Ignoring broken builds. Letting a build stay red for hours or days defeats the entire purpose of CI. It creates a polluted main branch and erodes trust in the system. The team needs to treat a red build as an emergency. Flaky tests, tests that pass and fail unpredictably, undermine the reliability of the CI system. They cause developers to ignore failures, leading to real bugs slipping through. Investing time in fixing flaky tests is crucial. Long-lived feature branches. While feature branches have their place, discussed in Chapter 4, if they are too long-lived, the integration efforts needed to pull them back into the main branch can resemble the very integration hell CI tries to avoid. Frequent, small integrations, even from feature branches, are key. Continuous integration is the beating heart of modern software delivery. By embracing frequent integration and immediate automated feedback, teams transform the complex, unpredictable chaos of traditional development into a predictable, high-quality, and confidence-inspiring process. It lays the essential groundwork for the next, equally powerful step, continuous delivery. Chapter Summary. Continuous integration. CI is a foundational software development practice where developers frequently integrate their code changes into a shared repository, with each integration verified by an automated build and automated tests. This process aims to detect and fix integration errors rapidly and consistently, leading to earlier bug detection, reduced integration headaches, and improved code quality. Key principles include maintaining a single source repository, automating builds and tests, triggering builds on every commit, and immediately addressing any failed builds. While the benefits are numerous, successful CI implementation requires comprehensive automated testing, a commitment to fixing broken builds instantly, and avoiding common pitfalls like infrequent integration or ignoring test failures. CI is the engine that drives continuous quality and builds the necessary confidence for faster software delivery. 4. Version control, the bedrock of collaborative development. Imagine trying to write an entire book with a team of authors, but each author only has their own copy of the manuscript. There's no central document, no way to track who made what changes, or to merge different versions effectively. The result would be a chaotic mess, a patchwork of conflicting narratives. In software development, your source code is the collective manuscript. Before you can even think about continuous integration or continuous delivery, you need a robust system to manage those lines of code, track changes, and enable multiple developers to work together without constantly clashing. This system is called version control. 4.1 The need for order. What is version control? At its core, a version control system, VCS, also known as a source code management, SCM, system is a tool that helps a team of software developers manage changes to source code over time. It records every modification to a file or set of files, creating a historical record that allows you to track changes, see who changed what, when, and why. Revert to previous versions. Go back to any point in the project's history if a mistake is made or a new change introduces problems. Collaborate effectively. Enable multiple developers to work on the same codebase simultaneously without overwriting each other's work. Identify issues. Easily pinpoint when a specific bug or behavior was introduced. Without a VCS, collaborative software development would be an unimaginable nightmare of manual file copies, email attachments, and constant communication to avoid overwriting each other's work. It would be brittle, slow, and prone to catastrophic errors. For CI/CD, a VCS isn't just helpful, it's the foundational layer upon which the entire automated pipeline is built. 4.2 Centralized versus distributed version control systems. Historically, there have been two main types of VCS. Centralized version control systems, CVCS. In a CVCS, like Subversion, SVN, or Perforce, there is a single, central server that contains the entire history of the project. Developers check out files from this central server to work on them and then check in their changes. Pros: simpler to understand for beginners, easier to manage permissions. Cons: single point of failure. If the server goes down, no one can work. Reliance on network connection. Merging can be complex when multiple people work on the same file. For CI/CD, the single point of failure and network dependency introduced fragility. Distributed version control systems, DVCS. In a DVCS, like Git, Mercurial, or Bazaar, every developer has a full, local copy of the entire repository, including its complete history. When developers push their changes, they are synchronizing their local repository with a remote one, often hosted on platforms like GitHub, GitLab, or Bitbucket. Pros: offline work. Developers can commit changes locally even without an internet connection. Speed. Most operations, committing, viewing history, are lightning fast because they happen locally. Resilience. No single point of failure. If the central remote server goes down, each developer still has a full copy. Robust branching and merging. DVCS, especially Git, excels at handling complex branching and merging scenarios, a critical feature for agile teams and CI/CD. Today, Git is the undisputed industry standard for version control. Its flexibility, performance, and powerful branching model make it exceptionally well-suited for modern, collaborative development, especially within a CI/CD context. Our discussion will primarily focus on Git due to its prevalence and advantages. 4.3 Key Git concepts for CI/CD. To understand how Git powers CI/CD, let's briefly touch upon its core concepts. Repository, repo. This is the project's central storage, containing all files, folders, and the complete history of changes. It's the master copy, or at least the primary remote copy. Commit. A commit is a snapshot of your changes at a specific point in time. Each commit has a unique identifier, a message explaining the changes, and links to its parent commits, forming a historical timeline. Making small, frequent, logical commits is a fundamental good practice for CI. Branch. A branch represents an independent line of development. When you create a branch, you're essentially creating a copy of your codebase at that moment. You can make changes on your branch without affecting the main codebase. Main, or trunk. This is typically the primary branch, representing the stable, shippable version of your software. In CI/CD, this branch is often considered deployable at any time. Feature branches. Developers often create short-lived branches to work on a specific new feature or bug fix in isolation. Merge or rebase. This is the process of combining changes from one branch into another. For instance, merging a feature branch back into the main branch once the feature is complete and tested. Push/pull. To synchronize your local repository with a remote repository. Push. Send your local commits to the remote repository. Pull. Fetch changes from the remote repository and merge them into your local branch. 4.4 Version control strategies in CI/CD context. The way a team uses version control profoundly impacts its ability to implement CI/CD. Two popular strategies stand out. Trunk-based development, TBD, concept. This strategy advocates for all developers to work on a single, shared main branch, the trunk. Instead of long-lived feature branches, changes are small, frequently committed, and directly integrated into the main branch. If feature isolation is needed, feature flags, toggles within the code to turn features on/off, are used. Advantages for CI/CD. High-frequency integration. Forces very frequent integration, often hundreds of times a day, which is the essence of CI. Minimal merge conflicts. Small, frequent changes mean fewer complex merge conflicts. Constant readiness. The main branch is always in a releasable state, making continuous delivery much easier. Suitability. This is considered the optimal strategy for mature CI/CD practices, as it fosters a culture of small, safe changes and continuous feedback. Short-lived feature branching. Concept. Developers create a dedicated branch for each new feature or bug fix. Once the work is complete, tested, and reviewed, often via a pull request or merge request, the feature branch is merged back into the main branch and then deleted. Advantages for CI/CD. Isolation. Allows developers to work on features without directly impacting the main branch until ready. Code review. Pull requests provide a formal mechanism for peer code review before integration. Suitability. While less continuous than strict TBD, if feature branches are short-lived, hours to a few days, and integrated frequently, this can still work very well with CI/CD. The key is not to have long-lived branches that diverge significantly from the main line. In both strategies, the goal is to integrate changes back into the main branch as frequently as possible. The longer a branch lives in isolation, the higher the risk of complex merge conflicts and the harder it becomes to integrate. 4.5. The role of version control in the CI pipeline. Version control isn't just where your code lives. It's the starting gun for your CI/CD pipeline. Triggering builds. The most common way to initiate a CI build is for the CI server to detect a new push, a commit to the version control repository. When new code arrives, the pipeline springs into action. Code accountability and traceability. Every change is attributed to a specific developer through commits. This allows for clear traceability. You can trace any line of code or any issue back to its source, its history, and who made the change. Foundation for rollback. If a deployment goes wrong or a bug makes it to production, the VCS provides the ability to quickly revert to a previous, known good version of the code. This forms a critical part of disaster recovery and quick fixes. Enabling collaboration. Developers can work on different parts of the same project or even the same file and use the VCS to manage the merging of their changes smoothly. Git's branching and merging capabilities are crucial here. Managing configuration and infrastructure as code, ISC. Beyond application code, CI/CD pipelines often involve managing environment configurations, deployment scripts, and even infrastructure definitions, e.g., cloud resources. Storing these in version control, as ISC ensures they are treated with the same rigor as application code, enabling automated provisioning and consistency. Think of your version control system, particularly Git, as the library of your software. It meticulously catalogs every single version of every single book, making it easy to find any addition, trace its evolution, and allow multiple librarians to add new books or update existing ones without chaos. Without this fundamental organization, a CI/CD pipeline simply cannot exist. It is truly the bedrock upon which all subsequent automated processes are built. Chapter Summary. Version control systems, VCS, especially Git, are the indispensable foundation for collaborative software development and the entire CI/CD process. They provide a robust mechanism for tracking and managing changes to source code, enabling multiple developers to work concurrently without conflict. Compared to older centralized VCS, distributed VCS like Git offer superior resilience, speed, and powerful branching capabilities. Key Git concepts such as repositories, commits, and branches are crucial for understanding modern development workflows. CI/CD benefits immensely from version control strategies like trunk-based development or short-lived feature branching, which promote frequent integration. Ultimately, the VCS acts as the primary trigger for the CI pipeline, provides traceability for all code changes, enables easy rollback, and facilitates the seamless collaboration essential for rapid, high-quality software delivery. 5. Automated testing, your safety net for quality. Imagine building a magnificent wooden bridge. You meticulously select the materials, design its elegant arches, and carefully assemble each piece. But you never test its load-bearing capacity. You never check if it can withstand high winds or if the wood will rot over time. Instead, you simply open it to traffic and hope for the best. This would be unthinkable for a physical structure, but it's precisely what happens in software development when automated testing is neglected. In the world of CI/CD, where speed and frequent releases are paramount, manual testing simply cannot keep up. Manual processes are slow, inconsistent, and prone to human error, creating a bottleneck that negates the benefits of automated builds and deployments. This is where automated testing steps in, acting as your ever-vigilant safety net, ensuring quality at every stage of the pipeline without slowing you down. 5.1. Why automated testing is non-negotiable in CI/CD. For CI/CD to truly deliver on its promise of rapid, reliable releases, every change must be verified quickly and thoroughly. Here's why automated testing is not merely a good idea, but an absolute necessity. Speed and efficiency. Automated tests can run thousands of checks in minutes, a feat impossible for human testers. This speed is critical for the rapid feedback loops that define CI. Consistency and reliability. Automated tests execute the exact same steps every single time. This eliminates human variability and ensures consistent test results, meaning you can trust a test failure to indicate a real problem. Regression prevention. As software evolves, new features can inadvertently break existing ones. Automated tests, especially regression tests, act as a safety net, instantly flagging such issues, known as regressions, before they impact users. Cost effectiveness. While there's an upfront investment in writing automated tests, they quickly pay for themselves by reducing the cost of finding and fixing bugs later in the development cycle, preventing costly production outages, and freeing up human testers for more complex, exploratory work. Confidence. Knowing that your tests will catch most common errors allows developers to commit new code with greater confidence, encouraging more frequent integrations and faster innovation. Think of automated tests as the continuous quality checks on a factory assembly line. Instead of waiting for the finished product to be inspected at the end, tests are run as each component is added, catching defects as early as possible. 5.2. The testing pyramid, a strategy for coverage. To implement effective automated testing, it's crucial to have a strategic approach. The testing pyramid, popularized by Mike Cohn, provides a visual metaphor for the optimal mix of different types of tests. Base, unit tests, largest and fastest. What they test: the smallest possible testable parts of an application, individual functions, methods, or classes, in isolation. They do not typically interact with databases, external services, or the user interface. Characteristics: extremely fast to run, milliseconds, highly isolated, and easy to write. You should have a large number of unit tests. Importance for CI: because they are so fast and pinpoint errors precisely, unit tests are the first line of defense in your CI pipeline. If a unit test fails, the build should fail immediately, providing rapid feedback to the developer. Middle integration tests, medium speed and number. What they test: the interactions between different components or modules. This might include testing the application's interaction with a database, external APIs, or other services. Characteristics: slower than unit tests, seconds, more complex to set up due to external dependencies, but provide better coverage of component interactions. Importance for CI/CD: these tests confirm that different parts of your system work together as expected. They are run after unit tests in the CI pipeline, often in a more realistic, though still automated, environment. Top. End-to-end E2E, test/UI tests, smallest and slowest. What they test: the entire system from a user's perspective, mimicking real user scenarios across the application's user interface. For example, a test that logs in, adds an item to a cart, and completes a purchase. Characteristics: the slowest to run minutes, most brittle can break easily with UI changes, and most expensive to maintain. Therefore, you should have the fewest eTWI tests. Importance for CI/CD. While valuable for overall system validation, these should be run later in the CD pipeline, e.g., in a staging environment due to their slowness. Relying too heavily on eTWI tests alone, an inverted pyramid anti-pattern, will make your CI/CD pipeline slow and unreliable. The principle is simple: more fast, specific, and cheap tests at the bottom. Fewer slow, broad, and expensive tests at the top. 5.3 Beyond the pyramid, other important test types. While the pyramid covers the functional core, a truly robust CI/CD pipeline incorporates other specialized automated tests. Performance testing, automated checks for system responsiveness, stability, and resource usage under various loads, e.g., load testing, stress testing. Crucial for ensuring scalability and user experience. Security testing, SAST DAST. Static application security testing, SAST. Scans source code for security vulnerabilities before execution. Dynamic application security testing, DAST. Tests the running application for vulnerabilities. Importance: shifting security left means integrating security checks early and often in the pipeline, rather than finding critical flaws just before release. Accessibility testing, automated checks to ensure the application is usable by people with disabilities. Compatibility testing, running tests across different browsers, operating systems, or device configurations. 5.4 Principles for effective automated tests in CI/CD. To ensure your automated tests are a blessing, not a burden, follow these principles. Fast. The quicker tests run, the more frequently you can get feedback. This is paramount for CI, reliable, deterministic. A good test should always produce the same result for the same input. Flaky tests that unpredictably fail or pass due to timing issues, environment dependencies, etc., erode trust and lead to engineers ignoring test results. Maintainable. Tests should be easy to understand, debug, and update as the application changes. Treat test code with the same quality standards as production code. Comprehensive. While avoiding 100% code coverage for the sake of it, tests should cover critical paths, known risks, and newly introduced functionality. Shift-left testing. The principle of test early, test often. The earlier in the development lifecycle a defect is found, the cheaper and easier it is to fix. Automated testing makes this possible. 5.5 Integrating tests into the CI pipeline. Automated tests are the gatekeepers at various stages of your CI/CD pipeline. Code commit. As soon as code is committed, the CI server automatically triggers the build and runs the incredibly fast unit tests. If any fail, the pipeline stops immediately, and the developer gets instant feedback. This is the fail-fast mechanism. Successful build. Once unit tests pass, the pipeline might proceed to run integration tests, perhaps against a temporary database or mock services. These tests are still relatively fast, but provide more confidence in component interactions. Deployment to staging test environment, CD. After a successful CI build, i.e., unit and integration tests passed, the application artifact is deployed to a staging or dedicated test environment. Here, slower but more comprehensive tests like eTWI tests, performance tests, and security scans are executed. Reporting results. The CI/CD system should clearly report the results of all test runs. This not only shows success or failure, but can also provide details like test coverage percentages, performance metrics, and security vulnerability reports. A critical aspect of CI/CD is that the pipeline halts if any crucial test fails. A red build, or a failed pipeline stage, immediately signals that a problem has been introduced and must be addressed before proceeding. No code should ever pass through the pipeline and reach users if it's failing automated tests. 5.6 The cultural shift, from QA gatekeepers to quality advocates. The rise of automated testing and CI/CD also ushers in a significant cultural shift for quality assurance. QA professionals. In traditional models, QA often acted as the final gatekeeper, manually testing software before release. While manual and exploratory testing remain vital, particularly for user experience and edge cases, the bulk of repetitive testing is now automated. This elevates the role of QA. Instead of solely finding bugs, QA professionals in a CI/CD environment become quality advocates and test automation engineers. Their focus shifts to designing robust test strategies, knowing what to test, how to test it, and which type of automated test is most appropriate. Building and maintaining automated test suites, developing and evolving the automated test infrastructure, coaching developers, helping development teams write better unit and integration tests themselves. Exploratory testing, using their human intuition to find subtle bugs and usability issues that automated tests might miss. Performance and security testing expertise, specializing in complex non-functional requirements. Ultimately, in a CI/CD culture, quality becomes everyone's responsibility, not just a department's. Developers are empowered to write tests. QA teams guide comprehensive test strategies, and the entire team works in concert to build quality into the very fabric of the software delivery process. Automated testing is the diligent sentinel that makes this continuous quality assurance possible. Chapter summary. Automated testing is the indispensable safety net for continuous integration and delivery, enabling rapid, reliable software releases by ensuring quality at every step. It offers speed, consistency, and efficient regression prevention, making it non-negotiable for modern software development. The testing pyramid guides a strategic approach, prioritizing numerous, fast unit tests at the base, followed by integration tests and a smaller number of end-to-end tests at the apex. Beyond functional tests, performance and security testing are critical. Effective automated tests must be fast, reliable, maintainable, and comprehensive, embodying the shift-left principle. These tests are meticulously integrated into the CI/CD pipeline, stopping progress immediately if any critical failures occur. This transition also fosters a cultural shift where quality becomes a shared responsibility, empowering QA professionals to evolve from manual gatekeepers to strategic test automation engineers and quality advocates. 6. The CI pipeline in action. From code to ready-to-deploy artifact. We've covered the why, the challenges of traditional software delivery, and the foundational ideas of Agile, DevOps, and the critical role of continuous integration and automated testing. Now, let's pull these threads together and see how they come to life in the engine room of modern software development, the continuous integration pipeline. The CI pipeline is the automated sequence of steps that transforms raw source code from a developer's commit into a tested, shippable product, ready for deployment. It's the automated assembly line for your software, ensuring that every change goes through a rigorous series of checks before it can progress further. 6.1 Inside the engine room. What is a CI pipeline? A CI pipeline is a series of automated processes and operations that run every time a change is introduced to the codebase. It's designed to build the software, run automated tests against it, and produce a deployable package, an artifact, providing rapid feedback on the quality and correctness of the change. Think of it as a quality control checkpoint that code must pass. Developers commit their code, and the pipeline immediately picks it up, putting it through its paces. If any stage fails, the pipeline stops, alerting the team to the problem before it can contaminate the main codebase or reach users. At the heart of the CI pipeline is the CI server, also known as a CI orchestrator or build server. Tools like Jenkins, GitLab CI/CD, GitHub Actions, Circle CI, Travis CI, and Azure DevOps are designed to automate these sequences. They monitor your version control system for changes, pull the code, execute predefined scripts, and report the results. 6.2 Anatomy of a typical CI pipeline stage by stage. While the exact steps in a CI pipeline can vary based on the language, technology, and complexity of the application, most share a common sequence of stages. Let's walk through a typical CI pipeline, stage by stage. Stage 1, Code checkout. Purpose: to fetch the latest version of the application source code from the version control system, VCS. Action: when a developer commits code or pushes to a shared remote repository, the CI server detects this change. It then fetches the latest code, often to a clean, isolated workspace, to ensure the build starts from a consistent state. This prevents "it worked on my machine" issues where builds might pass locally due to leftover files or specific configurations on a developer's machine, but fail in a clean environment. Stage 2. Build. Purpose: to compile the source code, resolve dependencies, and prepare the application for execution. Action: dependency resolution. The build tool downloads all necessary external libraries, frameworks, and modules that the application depends on. For example, a Java project might download jars from Maven Central, a Node.js project might install npm packages, or a Net project might restore NuGet packages. Compilation. The source code, e.g. Java, C, Go, C++, is compiled into executable binary code. For interpreted languages like Python or JavaScript, this stage might involve bundling, transpiling, or minifying the code. Static analysis/linting. Tools are run to analyze the code without executing it. This checks for coding style violations, potential bugs, security vulnerabilities, SASD, and adherence to best practices. This provides early feedback on code quality and maintainability. Output. If successful, this stage produces the compiled application components and ensures that the codebase is syntactically correct and can be assembled. Stage 3. Unit tests. Purpose: to quickly verify the correctness of individual, isolated components of the codebase. Action: the automated unit test suite is executed. As discussed in Chapter 5, these tests are fast, numerous, and should be highly reliable. Output: a report indicating the number of tests passed, failed, and often code coverage metrics. Criticality. This is a crucial fail-fast point. If any unit test fails, the pipeline should stop immediately, signaling that a defect was introduced and needs to be fixed before proceeding. Stage 4. Integration tests. Purpose: to verify that different modules or services within the application interact correctly with each other and with external dependencies, like databases or APIs. Action: automated integration tests are run. These are typically slower than unit tests and might require a minimal set of external services, often mocked or containerized temporarily, to be available. Output: a report on the success or failure of integration tests. Criticality. While not as fast as unit tests, these provide crucial confidence that the major components of your system can work together. A failure here also halts the pipeline. Stage 5. Create artifact. Purpose: to package the successfully built and tested application into a deployable unit. Action: the CI server creates an artifact, a specific, standardized package of the application that can be deployed to any environment. Examples: a Java jar or WAR file, a Docker image, a bundled set of JavaScript and HTML files, a Python wheel, a net assembly installer, etc. Immutability. Crucially, this artifact is immutable. This means the exact same artifact that passed all checks in the CI pipeline will be the one that is deployed to higher environments. Staging, production. No changes or modifications are allowed. Output: the deployable artifact, tagged with a unique version number, often derived from the commit hash or build number. Stage 6. Publish/store artifact. Purpose: to store the deployable artifact in a secure, versioned repository, making it available for subsequent deployment stages. Action: the created artifact is pushed to an artifact repository manager, e.g. Nexus, Artifactory, or cloud-specific registries like Docker Hub, Amazon ECR. Output: the artifact is now safely stored, with a record of its version and the build that produced it. Importance: this stage ensures that only artifacts that have successfully passed all CI checks are ever considered for deployment. It also serves as a central hub for managing and retrieving application versions, helping with traceability. 6.3 Key characteristics of an effective CI pipeline. Beyond the individual stages, a well-designed CI pipeline exhibits several key qualities. Fully automated, Every step from code checkout to artifact storage is automated. No manual intervention, no click hops. Fast feedback. It provides rapid feedback to developers on the quality of their changes. Ideally, a full CI run should complete within minutes. Reliable and consistent. The pipeline should consistently produce the same results for the same input. Flaky builds or tests undermine trust and adoption. Visible and transparent. The status of the pipeline, green-red, current stage, should be easily visible to the entire team, fostering shared responsibility. Self-testing. The definition of done for a CI build includes passing all automated tests. A build passing means the code is not only compiled, but also functionally sound according to the test suite. Reproducible builds. Anyone should be able to run the build process, locally or in a CI environment, and get the exact same artifact output. This is typically achieved through automated dependency management and containerization. Traceable. It should be easy to trace an artifact back to its source code, the specific commit that generated it, and the build that produced it. 6.4 What happens when the pipeline fails? Despite best practices, CI pipelines will inevitably fail sometimes. This isn't a problem, it's the benefit of CI. A failed pipeline indicates that a change has introduced a flaw. Immediate notification. When a stage fails, the CI server immediately notifies the relevant team members, often the person whose commit triggered the failure, and the entire team. These notifications might go to chat applications, Slack, Microsoft Teams, email, or dashboards. Stop the line mentality. As discussed in Chapter 3, the immediate response to a failed pipeline should be to stop working on new features and prioritize fixing the broken build. This ensures the main branch remains stable and always working. Troubleshooting and learning. Teams investigate the failure, identifying the root cause. This information is invaluable for learning and improving processes. For example, a new test might be added to prevent a recurrence of the bug, or a problematic coding pattern might be identified. Fix and retrigger. Once the issue is resolved, either by reverting the change or applying a fix, the developer commits the fix, and the pipeline is retriggered to confirm the problem is resolved. 6.5 Tools of the trade. Conceptual roles, not configurations. While we avoid deep dives into specific tool configurations, it's helpful to understand the conceptual roles of popular CI tools. CI servers/orchestrators. These are the brains of the operation. They monitor repositories, execute pipeline stages, manage build agents, and report results. Examples: Jenkins, GitLab CI/CD, GitHub Actions, Circle CI, Travis CI, Azure DevOps. Build automation tools, used within the pipeline stages to compile code, run tests, and package applications. Examples: Maven Gradle Java, NPM Yarn JavaScript, MSBuild .NET CLI.NET, Make test frameworks for writing and running the actual tests. Examples: JUnit TestNG Java, Jest Mocha JavaScript, NUnit XUnit Net, PyTest Python. Artifact repositories for storing the output of successful builds. Examples: Nexus Repository Manager, Artifactory, Amazon S3, Azure Blob Storage for generic storage. Containerization tools, increasingly used to create isolated, reproducible build environments and to package applications into immutable Docker images. Example: Docker. The continuous integration pipeline is a powerful mechanism for building quality into your software. It takes the principles of frequent integration and automated testing and orchestrates them into a seamless, high-confidence process. Once your CI pipeline is consistently producing a high-quality, ready-to-deploy artifact, you've set the ultimate stage for the next transformation. Continuous delivery. Chapter summary. The continuous integration. CI pipeline is the automated sequence of steps that transforms source code into a tested, deployable artifact. Orchestrated by a CI server, it typically involves stages such as code checkout, compilation build, automated unit tests, integration tests, artifact creation, packaging and immutable deployable, and artifact storage. The purpose of this pipeline is to provide rapid feedback on code quality, ensure integration errors are caught quickly, and produce a consistently high-quality, shippable product. An effective CI pipeline is fully automated, fast, reliable, visible, and self-testing. When a pipeline fails, it signals a problem that must be fixed immediately, emphasizing a stop-the-line mentality to maintain a stable codebase. Various tools facilitate these stages, ranging from orchestrators to build tools and artifact repositories, all contributing to making the CI pipeline the engine room for building quality into software. 7. Continuous delivery, bridging the gap to production. In the previous chapter, we explored the CI pipeline, which takes your code from a developer's commit to a ready-to-deploy artifact. This is a massive step forward, transforming the initial chaotic maze into a well-oiled assembly line for building and testing. But having a thoroughly tested, deployable artifact isn't enough to get new features into the hands of users rapidly. That final hurdle, getting the software deployed to a production environment, remains. Consider our car analogy. Continuous integration ensures your car is mechanically sound. All parts are working independently and together, and it's fueled up and ready for a journey. But continuous delivery is about ensuring that car is packed, the GPS is set, and it's sitting in the driveway, ready to hit the road at a moment's notice, whenever you decide to leave. The decision to actually drive off is still yours. 7.1 Beyond CI, what is continuous delivery, CD? Continuous delivery, CD, is an extension of continuous integration. It's a software engineering approach where teams produce software in short cycles, ensuring that the software can be reliably released at any time. The core principle of CD is that your code should always be in a deployable state, meaning it has passed a comprehensive set of automated tests and is consistently ready to be pushed to a production environment safely and quickly. The critical distinction from CI is that CD validates the deployability of the code. It builds upon CI's automated testing by adding more stages of automated verification and, crucially, automating the deployment process itself to various environments leading up to production. The ultimate deployment to a live production environment remains a manual, human-triggered decision, but the mechanism to do so is entirely automated. This means that if a business decides that a new feature needs to go live today, the team can confidently deploy the latest working version of the software with a push of a button, rather than having to scramble for days or weeks to prepare a release. 7.2 The CD pipeline, extending the CI journey. The CD pipeline is essentially an extension of the CI pipeline, adding more stages after the artifact has been created and stored. It represents the flow of value from development to production. Let's expand on our previous CI pipeline stages. Stage 1 to 6 CI stages: code checkout, right arrow build, right arrow unit tests, right arrow integration tests, right arrow create artifact, right arrow publish artifact. These stages ensure the artifact is technically sound and has passed core automated checks. Stage 7, automated testing, advanced/environment specific. Purpose: to run more extensive, time-consuming automated tests on a production-like environment. Action: once the artifact is available, it is automatically deployed to a dedicated staging, quality assurance, QA, or pre-production environment. Here, a broader suite of automated tests is executed: end-to-end E2E tests, verifying user journeys across the entire application, see Chapter 5. Performance tests, assessing application responsiveness, scalability, and stability under simulated load. Security scans, automated checks for vulnerabilities in the deployed application, DASD, dynamic application security testing. Usability accessibility tests, automated checks for user experience and compliance. Key aspect: the environment should be as close to production as possible in terms of configuration, data, and infrastructure. Stage 8, user acceptance testing, UAT/exploratory testing, human gate. Purpose: to allow non-technical stakeholders, product owners, business users, QA specialists, to manually verify the application meets business requirements and performs as expected in a production-like setting. Action: after all automated tests pass in the staging environment, the application is presented to human testers. This is typically the only manual gate in a truly continuous delivery pipeline. Importance: while automation is key, human intuition can catch subtle usability issues, context-specific bugs, or unexpected behavior that automated tests might miss. This feedback loop is crucial. Stage 9. Release approval, manual decision point. Purpose: to make the final decision to deploy the artifact to production. Action: this stage represents the explicit, human-driven decision to initiate a production deployment. The pipeline may pause here, waiting for a user to click a Deploy to Production button. This decision should be backed by successful execution of all previous automated and manual tests, review of test reports, performance metrics, and security scan results, business readiness assessment. Automation role: while the decision is manual, the process to get to this decision point is automated, and the subsequent deployment, Stage 10, is also automated. Stage 10, automated deployment to production. Purpose: to deploy the application to the live production environment reliably and efficiently. Action: once approved, the exact same artifact that passed all previous stages is automatically deployed to production. This stage often incorporates advanced deployment strategies to minimize downtime and risk. Blue-green deployments: two identical production environments, blue and green. One is live, the other is for new deployments. Traffic is switched instantly when the new version is ready. Canary releases: deploying the new version to a small subset of users or servers first, monitoring closely, and gradually rolling it out to more users. Rolling updates: updating servers sequentially to maintain service availability during the update. Infrastructure as code, ISC. This stage heavily relies on ISC to ensure environments are consistent and reproducible. Stage 11. Post-deployment verification, automated. Purpose: to quickly confirm that the application is running correctly in production after deployment. Action: automated smoke tests or health checks are performed immediately after deployment to ensure the application starts up, provides basic services, and responds to critical requests. This is a final safety check. 7.3 Key Principles of Continuous Delivery. Embracing CD means adhering to principles that ensure reliability and readiness. Deploy anything, anytime. The ultimate goal is that the team can confidently release the software at any time they choose, without significant manual effort or anxiety. Automate everything feasible. Minimize manual intervention wherever possible. If a step is repetitive, automate it. Build on demand, deploy on demand. It's not about always deploying, it's about being able to deploy. Identical environments. Dev, QA, staging, and production environments should be as identical as possible to prevent works on my machine or works in staging issues. Infrastructure as code is critical here. Immutable artifacts. The same deployable artifact that gets built and tested in CI is the one that gets deployed to all environments. No modifications allowed. Rollback/roll-forward capability. If something goes wrong in production, you must have the automated ability to quickly revert to the previous working version rollback or apply a rapid fix roll-forward. 7.4 Benefits of continuous delivery. The advantages of a mature CD pipeline are transformative for an organization. Rapid and reliable releases, reduced deployment risk and effort, making releases routine and less stressful. Faster time to market. New features, bug fixes, and innovations reach users and customers much faster, providing immediate business value. Lower risk deployments. Smaller, more frequent changes are inherently less risky than large, infrequent, big bang releases. If an issue occurs, it's easier to pinpoint and fix or roll back. Faster feedback from real users. Getting new features into production quickly allows for immediate user feedback, enabling quicker iteration and ensuring you're building what users truly need. Improved business agility. The ability to respond quickly to market changes, competitive threats, or new opportunities provides a significant competitive advantage. Elimination of deployment anxiety. Releases become a non-event, fostering a calmer, more confident team and allowing them to focus on innovation. 7.5 Challenges and considerations for CD. Implementing CD is a significant undertaking and comes with its own set of challenges. Environment management. Ensuring environments are consistent and stable across the pipeline, especially non-production ones, is complex. Tools like containerization, Docker, Kubernetes, and infrastructure as code help immensely. Data management, managing test data, refreshing production data in lower environments, and ensuring data privacy and security can be a significant hurdle. Legacy systems, integrating older applications or systems that weren't designed for automated, continuous deployment can be challenging. Dependency management, for microservices architectures, orchestrating deployments across multiple interdependent services while maintaining compatibility requires careful planning. Security and compliance, integrating robust security checks and maintaining an audit trail throughout the continuous deployment process is crucial, especially in regulated industries. Tooling complexity. Setting up and maintaining a sophisticated CD pipeline often involves a suite of tools, which can have a steep learning curve. The key is to keep it simple and grow it incrementally. Continuous delivery represents a significant leap forward in software delivery, turning the painful final stage into a predictable, automated process. By continually preparing software for release, organizations gain unprecedented flexibility, speed, and confidence in their ability to deliver value. It's the essential bridge connecting the developer's workstation to the user's screen, ready for the next step: full continuous deployment. Chapter summary. Continuous delivery, CD, extends continuous integration by ensuring that software is always in a deployable state, ready for release at any time. While the ultimate deployment to production remains a manual decision, the entire process leading up to it is automated. The CD pipeline encompasses CI stages, adding further automated testing, E2E, performance, security on production-like environments, a human gate for user acceptance testing, UAT, a manual release approval step, and finally, automated deployment to production with strategies like blue-green or canary releases. Key principles include automating everything feasible, maintaining identical environments, using immutable artifacts, and having robust rollback capabilities. The benefits are significant: faster, lower-risk releases, improved time to market, increased business agility, and reduced deployment anxiety. Challenges include environment and data management, handling legacy systems, and managing tooling complexity, but these are overcome by carefully planning and adopting principles like infrastructure as code. CD acts as the crucial bridge that connects tested code directly to the readiness for production deployment. 8. Continuous deployment, taking the leap to automated releases. We've ascended from the chaotic maze of traditional software delivery, through the ordered process of continuous integration, to the point where our software is always ready for release with continuous delivery. Now we stand at the peak of the mountain, ready to take the ultimate leap: continuous deployment. Recalling our car analogy from the previous chapter, continuous delivery ensures your car is packed and ready to go at a moment's notice, waiting for you to decide when to leave. Continuous deployment takes it one step further. The GPS is set, the car is packed, and as soon as it's ready, it drives itself to the destination without any human intervention. 8.1. The ultimate goal. What is continuous deployment, CD? Continuous deployment, CD, is the natural evolution of continuous delivery. In a system practicing continuous deployment, every change that successfully passes all stages of the automated pipeline is automatically released to production. There is no manual gate, no human decides when to deploy. If the code builds, tests, and passes all automated quality checks, it goes live. This is the fastest possible way to get changes into the hands of users. It removes the human click between a fully verified build and its appearance in the live environment. This means new features, bug fixes, and improvements are deployed as soon as they are ready, sometimes multiple times a day or even dozens of times an hour. The term continuous deployment is often used interchangeably with continuous delivery, leading to confusion. It's crucial to differentiate continuous delivery. The software is always deployable to production, and the deployment can be triggered manually. Continuous deployment. The software is always deployed to production automatically after passing all automated tests. 8.2. When is continuous deployment appropriate, and when is it not? While continuous deployment offers incredible agility, it's not a universal panacea for every organization or every application. It requires a significant level of maturity and trust in your automated processes. Continuous deployment is most appropriate for web applications and SaaS products, where updates can be pushed frequently without involving physical hardware or app store reviews. Highly iterative products. Companies that thrive on rapid experimentation, A/B testing, and immediate feedback from users, e.g., consumer tech companies like Google, Netflix, Amazon. Mature teams with high automation. Organizations that have invested heavily in comprehensive automated testing, robust monitoring, and have a blameless culture that values learning from failures. Low barrier to recovery. Systems where an issue can be quickly identified and a rollback fix can be deployed almost instantly with minimal impact. Continuous deployment might be less suitable for highly regulated industries initially, while some highly regulated industries, e.g., finance, healthcare, are moving towards CD. It often requires significant effort to ensure audit trails and compliance can be fully automated and trusted by regulatory bodies. Manual approval gates might still be legally mandated for certain releases. Critical systems with severe consequences of failure. Applications where a bug could have devastating impacts, e.g., medical devices, aerospace systems, might require an additional human review, at least until an extremely high level of confidence in the automation is achieved. Organizations just starting their CI/CD journey. Jumping straight to continuous deployment without first mastering continuous delivery and robust automated testing is akin to trying to fly without walking. It often leads to more pain than gain. 8.3 Enabling continuous deployment, prerequisites and pillars. To achieve the nirvana of continuous deployment, several prerequisites must be firmly in place and continually reinforced. Comprehensive automated testing, absolutely critical. This cannot be overstated. With no human gate, your automated tests are the only safety net. You need exceptionally high-quality unit, integration, and end-to-end tests without any flakiness. Every critical scenario must be covered. Robust monitoring and alerting. You need to have an unparalleled ability to observe your application's behavior in production. This includes logging, centralized, searchable logs for detailed insights, metrics, real-time data on performance, resource usage, and application health, tracing, understanding how requests flow through distributed systems, automated alerting, notifications for any deviations from normal behavior, allowing immediate detection of issues without human vigilance. Fast and reliable rollback/roll forward. When an issue inevitably slips through, no system is perfect. You must have the automated capability to roll back, instantly revert to the previous known good version of the application. Roll forward. Quickly deploy a hotfix that addresses the issue. Your deployment strategies, blue, green, canary, facilitate this. Small, incremental changes. The smaller the change, the easier it is to pinpoint a problem if one arises, and the smaller the blast radius of that problem. Large, infrequent changes are anathema to continuous deployment. Mature infrastructure as code, ISC. Your environment's development, staging, production must be consistent, reproducible, and provisioned automatically. This ensures that what works in one environment will work in another. Strong, blameless culture. Failures will happen. A blameless culture focuses on quickly identifying the root cause, learning from the incident, and implementing preventative measures rather than assigning blame. This psychological safety encourages innovation and transparency. 8.4 Strategies for safe continuous deployment. Automating releases to production doesn't mean blindly pushing code. Advanced deployment strategies are essential to mitigate risk. Feature flags/feature toggles. Concept allows you to deploy new code to production with the feature turned off. The feature can then be enabled or disabled dynamically for specific users or groups without requiring a new code deployment. Benefit: decouples deployment from release. You can deploy code multiple times a day, but only release a feature when ready, mitigating risk. Enables A/B testing and dark launches. Canary deployments. Concept: the new version of the application is deployed to a very small subset of your users or servers, the canary in the coal mine. Their experience is closely monitored. If stable and performing well, the new version is gradually rolled out to the rest of the user base. Benefit: limits exposure to potential issues, allows for real-world testing with a small impact. Blue-green deployments. Concept: you maintain two identical production environments. Blue, the current live version, and green, the new version. The new version is deployed to the green environment, tested thoroughly, and then user traffic is instantly switched from blue to green. Benefit: provides zero downtime deployments and an immediate rollback mechanism by simply switching traffic back to blue if issues arise. Rolling updates. Concept: for applications running on multiple servers or containers, the new version is deployed incrementally, one server at a time or in small batches. This ensures that the application remains available throughout the update process. Benefit: maintains service availability, but rollback can be slower than blue-green. Automated remediation. Concept: if monitoring systems detect a problem after a deployment, the pipeline can be configured to automatically trigger a rollback to the previous version or execute another predefined recovery action. Benefit: dramatically reduces mean time to recovery, MTTR, and minimizes the impact of production incidents. 8.5 The payoff. Why strive for continuous deployment? The benefits of reaching continuous deployment are profound and deliver immense value. Maximum velocity. New features and bug fixes reach customers at the fastest possible speed, maximizing business agility and responsiveness to market changes. Happier customers. Users receive improvements and problem resolutions instantly, leading to higher satisfaction and engagement. Reduced waste. Eliminates the time and effort spent on manual gates, release planning, and coordinating large, infrequent deployments. True agility. Organizations can pivot and adapt strategies almost in real time based on market feedback and data, gaining a significant competitive edge. Continuous learning. The rapid deployment cycle provides immediate feedback, allowing teams to learn quickly about their features, iterate faster, and continuously improve their product and processes. Increased team morale. Developers and operations personnel can focus on innovation and value creation, instead of being burdened by the stress and toil of infrequent, high-risk releases. 8.6 Overcoming the fear factor. Transitioning from continuous delivery to continuous deployment is often a journey of cultural change and building trust. The idea of releasing directly to production without human review can be daunting. Overcoming this fear requires trust in automation. This trust is built through years of diligently writing comprehensive tests, perfecting monitoring, and practicing continuous delivery flawlessly. Gradual rollout. Start small, perhaps with a less critical service or just a subset of user traffic, and gradually expand the scope of continuous deployment as confidence builds. Blameless postmortems. When incidents occur, use them as learning opportunities to improve the system and processes, reinforcing a culture of collaboration over blame. Continuous deployment is not just a technical process. It's a statement of confidence in an organization's engineering practices and culture. It represents the pinnacle of efficient, reliable, and rapid software delivery, ensuring that innovation flows seamlessly from concept to customer. Chapter summary. Continuous deployment is the ultimate evolution of the automated delivery pipeline, where every change that successfully passes all automated tests is automatically released to production without human intervention. While not suitable for every context, it is ideal for highly iterative applications and mature teams with robust automation. Key prerequisites include exceptionally comprehensive automated testing, robust monitoring and alerting, fast rollback capabilities, small incremental changes, and a strong blameless culture. Strategies like feature flags, canary deployments, blue-green deployments, and automated remediation are vital for managing risk in a continuous deployment environment. The payoff is immense. Maximum velocity, happier customers, reduced waste, and true business agility. Overcoming the inherent fear factor requires building deep trust in automation, gradual implementation, and a strong, blameless culture, ultimately reaching the pinnacle of modern software delivery. 9. Monitoring and feedback, completing the loop. We've explored how CI/CD enables teams to build, test, and deliver software with incredible speed and confidence. But what happens after the software is successfully deployed to production? The journey doesn't end there. In fact, for a truly continuous and improving delivery process, the post-deployment phase, how the software performs in the real world, is just as critical as the preceding stages. This is where monitoring and feedback come into play, completing the infinite loop of the DevOps lifecycle. Imagine launching a satellite into orbit. You've meticulously designed it, built it with precision, and launched it perfectly. But if you have no way to track its trajectory, measure its health, or receive data from its sensors, how would you know if it's performing as expected, or if it's drifting off course before it's too late? In the same way, simply deploying software without robust monitoring is akin to launching a rocket and hoping for the best. 9.1. The need for observability. Knowing what's happening in production. In a CI/CD world, where changes are pushed to production at high velocity, waiting for a customer to report an error is simply unacceptable. You need to know about problems before your users do. This is the essence of observability, the ability to infer the internal state of a system based on its external outputs. It's about having enough data about your running application to truly understand its behavior, diagnose issues, and make informed decisions. Observability encompasses more than just traditional monitoring. While monitoring tells you if a system is working, e.g., CPU utilization, disk space, observability helps you understand why it isn't working by allowing you to ask arbitrary questions about its internal state. The primary streams of data for observability are metrics, numerical values measured over time. These are typically aggregated data points about the system's performance and health. Examples: CPU usage, memory consumption, request latency, error rates, transactions per second, number of active users. Logs, time-stamped records of discrete events that occurred within the application or system. These provide context about what happened when. Examples: user login events, error messages, system shutdowns, database queries. Traces represent the end-to-end flow of a single request or transaction as it propagates through various services and components, especially critical in microservices architectures. They show the path and timing of execution across distributed systems. 9.2. Core monitoring areas in CI/CD. For a robust CI/CD pipeline, monitoring extends beyond just the application itself to encompass the entire delivery process. 9.2.1. Application Monitoring, APM. Purpose: to understand the performance, health, and user experience of your live application. What to monitor? Availability. Is the application up and running? E.g., uptime, synthetic transactions. Performance: how fast are user requests? E.g., response times, throughput, latency. Error rates: how many errors are users encountering? E.g., HTTP 5xx errors, application exceptions. Resource utilization: how efficiently is the application using CPU, memory, disk, network? Business metrics. Key performance indicators, KPIs relevant to the business, e.g., conversion rates, number of active users, shopping cart abandonment. Tools: Datadog, New Relic, AppDynamics, Prometheus/Grafana, Splunk, Elastic Stack Elk. 9.2.2. Infrastructure monitoring. Purpose: to ensure the underlying infrastructure, servers, containers, databases, networks, supporting your application is healthy and performing optimally. What to monitor? CPU usage, memory utilization, disk I/O, network traffic, server temperatures, database query performance, container health, cloud resource consumption. Tools: Zabbix, Nagios, Prometheus/Grafana, cloud-specific monitoring, AWS CloudWatch, Azure Monitor, GCP operations. 9.2.3. CI/CD pipeline monitoring. Purpose: to track the health and efficiency of your continuous integration and delivery pipelines themselves. What to monitor? Build success rate, percentage of successful CI builds. Build duration, how long each stage and the overall build takes. Deployment frequency, how often code is deployed to production. Lead time for changes, time from code commit to production deployment. Change failure rate, percentage of deployments that cause an incident. Mean time to recovery, MTTR. How long it takes to recover from a production incident. Tools, built-in dashboards of CI/CD platforms, GitLab CI/CD, GitHub Actions, Jenkins, custom dashboards using metrics from these platforms injected into Prometheus/Grafana. 9.3 Alerts, dashboards, and visualizations. Monitoring is only useful if the data is actionable. Alerting, define thresholds for metrics or specific log patterns that trigger notifications to teams. Alerts should be actionable and sent to the right people, e.g., on-call engineers for critical issues, development team for application-level errors. Over-alerting, alert fatigue, is a common problem to avoid. Dashboards, visual representations of key metrics and logs, providing a real-time overview of system health and performance. Teams can use these to quickly identify trends, bottlenecks, or anomalies. Visualizations, graphs, charts, and heat maps that help absorb complex data at a glance, making it easier to spot patterns and dive deeper into problem areas. 9.4 The critical role of feedback loops in DevOps. Monitoring provides the data, but feedback loops transform that data into actionable insights and continuous improvement. Feedback loops are the essence of the Operate Right Arrow Monitor Right Arrow plan, part of the DevOps cycle. Automated feedback. Pipeline gates, automated tests and quality checks within the pipeline are immediate feedback loops. A failing test provides instant feedback to the developer. Rollback/roll forward, automated actions triggered by post-deployment monitoring, e.g., automatic rollback if production health checks fail. Human feedback. Alerts to teams, prompt engineers to investigate and resolve issues. Postmortems/blameless retrospectives. When an incident occurs or a major failure happens in the pipeline, the team conducts a blameless postmortem. The focus is on what happened, why it happened, and what can be learned to prevent recurrence, rather than blaming individuals. This leads to continuous improvement of processes, tools, and code. User feedback. Directly from customers, e.g., support tickets, feature requests, usage analytics. The fast deployment facilitated by CI/CD allows teams to rapidly iterate on this feedback. A/B testing and canary releases. These are direct feedback mechanisms, using real user behavior and system performance to inform decisions about new features or versions. 9.5 Shift right for better monitoring and observability. While shifting left, doing things earlier in the development lifecycle, like security scanning, is a crucial CI/CD principle, monitoring and observability also involve a shift right approach. This means thinking about how to observe and measure your application in production from the very beginning of the design phase. It involves instrumenting your code with the right metrics and logs, ensuring your infrastructure is monitored effectively, and planning for how you will understand your system's behavior once it's live. This shift right also implies that operations and development teams are equally invested in production health, monitoring, and responding to incidents collaboratively. It tears down the traditional, throw-it-over-the-wall mentality, fostering a shared responsibility for the entire system lifecycle. 9.6 Completing the DevOps loop. Monitoring and feedback loops are not just an add-on. They are integral to the very definition of DevOps and continuous improvement. Operate, deploy the software to production. Monitor, collect data on its performance, health, and user experience. Learn feedback. Analyze the data, identify problems, gain insights from incidents and user behavior. Plan, use these insights to inform the next iteration of development, fixing bugs, building new features, improving infrastructure. Code. And the loop continues. This continuous cycle of building, deploying, monitoring, learning, and planning ensures that the organization is not just delivering software, but also continuously improving the software and the process of delivering it. It creates a robust, self-correcting system that thrives on information and adaptation, making the entire CI/CD pipeline stronger and more resilient over time. Without effective monitoring and robust feedback loops, even the most efficient CI/CD pipeline is running blind, risking instability and lost opportunities. Chapter summary. Monitoring and feedback are crucial for completing the continuous integration and delivery CI/CD loop. ensuring that software performs as expected in production and that teams continuously learn and improve. Observability, the ability to understand a system's internal state from its outputs, is paramount, relying on a combination of metrics, logs, and traces. Effective monitoring encompasses application performance monitoring, APM, infrastructure monitoring, and crucial CI/CD pipeline monitoring, e.g., build success rates, lead time, change failure rate. Actionable insights are derived through intelligent alerting, comprehensive dashboards, and clear visualizations. Feedback loops, both automated, e.g., pipeline gates, auto rollback, and human, e.g., blameless postmortems, user feedback, are critical for identifying issues, learning from incidents, and informing future development. This shift right in thinking ensures that operational concerns are considered from the design phase, fostering shared responsibility for production health and enabling a truly continuous and improving delivery cycle. 10. The human element, culture, collaboration, and change management. Throughout this book, we've explored the technical marvels of continuous integration and delivery. Automated builds, comprehensive testing, seamless deployments, and robust monitoring. We've seen how these practices transform the chaotic maze of traditional software delivery into a smooth, efficient pipeline. However, no matter how sophisticated the tools or how perfect the pipelines, CI/CD is fundamentally a human endeavor. Its success hinges less on the technology itself and more on the people who design, build, operate, and maintain it. Think of it this way: you can buy the most advanced, fully automated car factory in the world. But if the engineers don't collaborate, if the management doesn't foster innovation, and if the workers are resistant to change, that factory will never produce cars efficiently or safely. Similarly, CI/CD is not just about installing software. It's about transforming mindsets, fostering collaboration, and managing the inevitable changes that ripple through an organization. 10.1 Culture is king. The foundation of DevOps. At its core, CI/CD is enabled by culture. As we discussed in Chapter 2, DevOps is rooted in a cultural shift, a movement away from siloed teams and towards shared responsibility and collaboration. This culture manifests in several key ways: shared responsibility and empathy. No more throw it over the wall. Developers consider the operational impact of their code, and operations teams understand the pressures of rapid feature delivery. Everyone feels a sense of ownership for the entire software delivery lifecycle, from idea to production and beyond. Blameless culture. When things go wrong, and they will, the focus shifts from finding fault to understanding why the failure occurred and how to prevent it in the future. Postmortems are opportunities for learning and improvement, not for blaming individuals. This psychological safety empowers teams to experiment and innovate without fear of retribution. Automation mindset. There's a persistent drive to automate repetitive, manual tasks. If a human has to click a button more than once, it should be automated. This frees up staff for more creative, complex, and value-adding work. Continuous improvement. The culture embraces constant learning and adaptation. Feedback loops, as discussed in Chapter 9, are cherished, and teams are empowered to analyze data, identify bottlenecks, and continuously refine their processes and tools. Open communication and transparency. Information flows freely through the organization. Dashboards are visible, pipeline statuses are known, and discussions happen openly. This reduces ambiguity and fosters alignment. Without these cultural underpinnings, CI/CD tools can become white elephants installed but rarely used effectively, or worse, used in a way that perpetuates old problems instead of solving them. 10.2 Collaboration. Breaking down the silos. CI/CD inherently demands collaboration between different roles and departments that were traditionally separated. Dev and Ops, better together. The DevOps ideal is achieved through shared goals, shared tooling, and shared on-call responsibilities. For example, developers might contribute to operational runbooks, and operations engineers might provide feedback on application architecture early in the development cycle. Development and QA. Quality built-in. The adversarial relationship between developers and QA teams transforms into a partnership. Developers actively write tests and are responsible for the quality of their code. QA professionals evolve into test automation specialists, performance testers, and quality coaches, working alongside developers to guide test strategies and ensure comprehensive coverage. Business and technology, shared objectives. CI/CD brings the business closer to the technology. Rapid feedback loops and frequent deployments mean new features and business ideas can be quickly validated with real users. This fosters a shared understanding of business value and technical feasibility, enabling quicker adjustments to market demands. Tools like shared communication channels, Slack, Microsoft Teams, collaborative documentation platforms, and visual dashboards all facilitate this increased interaction. Even physical co-location or structured team pairings can dramatically improve collaboration. 10.3 Change management, guiding the transformation. Implementing CI/CD is not a flip of a switch. It's a profound organizational change. Effective change management is crucial to ensure smooth adoption and avoid resistance and failure. Start with why. Before introducing new tools or processes, explain the why. Articulate the pain points the old ways caused and the specific benefits CI/CD will bring, e.g., less stressful releases, faster feedback, reduced toil, more innovation. People are more likely to embrace change if they understand how it benefits them personally and professionally. Leadership buy-in and sponsorship. Change must be driven from the top. Leaders need to visibly support the CI/CD initiative, allocate necessary resources, and champion the new way of working. Their commitment helps overcome inertia and provides direction. Identify champions and early adopters. Find enthusiastic individuals or teams who are eager to embrace CI/CD. Let them lead the way, demonstrate success, and act as internal evangelists and trainers for others. Their positive experiences are powerful motivators. Invest in training and skill development. CI/CD often requires new skills: automated testing, pipeline scripting, containerization, cloud infrastructure. Provide adequate training, workshops, and learning resources. Emphasize continuous learning as a core value. Start small, show success, iterate. Don't try to change everything at once. Pick a small, non-critical project or team as a pilot. Demonstrate tangible successes and then gradually expand CI/CD adoption across the organization. Learn from early mistakes and continuously adapt the implementation strategy. Communicate continuously and celebrate wins. Keep everyone informed about progress, challenges, and successes. Celebrate milestones: successful automated deployments, reduced build times, a decrease in production incidents. Recognition reinforces positive behavior. Address resistance and concerns. Listen to feedback. Understand concerns about job security, learning new skills, or potential issues. Address these empathetically and transparently. Show how new tools create new opportunities rather than eliminate existing roles. Consider the case of a large enterprise, Global Tech Inc., which decided to adopt CI/CD. Their initial approach was to mandate a new CI server and train everyone on its features. Unsurprisingly, this met with significant passive resistance. Developers continued old habits, operations teams viewed the DevOps engineers as a separate silo, and releases remained painful. Only when leadership shifted their focus to cultural change did things begin to improve. They redefined team structures to be cross-functional, encouraged shared metrics, implemented blameless postmortems, and created internal DevOps coaches who helped teams gradually adopt practices. They made the journey visible, celebrating small victories like the first fully automated staging deployment or a 50% reduction in build times. It was a slow, deliberate process, but eventually, Global Tech Inc. transformed from a release-dreading organization to one that deployed multiple times a week with confidence. Their success wasn't due to the CI server, it was due to the people. 10.4 Cultivating the DevOps mindset for continued success. The CI/CD journey is never truly finished. It's a continuous process of improvement. Cultivating a DevOps mindset within the organization means embedding these principles into daily operations. Experimentation. Encourage teams to try new tools and processes and to learn from both success and failure. Feedback-driven improvement. Treat every incident, every slowdown, every complaint as an opportunity to pinpoint areas for enhancement. Systems thinking. Encourage everyone to understand how their work fits into the larger value stream and to optimize for the whole system, not just their individual part. Embracing automation. See automation not as a threat, but as a liberator from tedious, repetitive work, allowing humans to focus on higher value tasks. The human element is not a challenge to be overcome in CI/CD. It is the catalyst for its success. No matter how advanced the technology, it is the collaboration, the culture, and the willingness to embrace change within your teams that will ultimately define the effectiveness and longevity of your continuous integration and delivery transformation. Chapter summary. While CI/CD relies heavily on automation and technical processes, its ultimate success is determined by the human element. Culture, collaboration, and change management. A supportive culture is paramount, fostering shared responsibility, empathy, a blameless approach to failures, and a continuous improvement mindset. Breaking down traditional silos is crucial. CI/CD demands close collaboration between development and operations, DevOps, development and QA, quality built-in, and technology and business, shared objectives. Implementing CI/CD is a significant organizational change requiring thoughtful management. Communicate the why, secure leadership buy-in, identify champions, invest in training, start small, celebrate successes, and address resistance empathetically. Cultivating a continuous DevOps mindset, driven by experimentation and feedback, ensures that CI/CD remains a dynamic and effective practice, prioritizing the human capacity to innovate and adapt. 11. Navigating the landscape, tools, trends, and advanced practices. By now, you have a solid understanding of the why and what of CI/CD, from its foundational principles in Agile and DevOps to the practical mechanics of build pipelines and the critical human elements. While this book consciously avoids deep dives into specific tool configurations, which can quickly become outdated, it's crucial to understand the broader ecosystem of tools that enable CI/CD, as well as emerging trends and advanced practices that are shaping the future of software delivery. Think of it as navigating a vast, ever-evolving landscape. You need a map, our principles and practices, but you also need to know about the different modes of transport tools and potential new frontiers trends to make your journey efficient and future-proof. 11.1 The CI/CD tool ecosystem, players and their roles. The CI/CD landscape is rich and dynamic, with countless tools available, ranging from open-source projects to commercial enterprise solutions. They generally fall into several key categories, often with overlapping capabilities. 11.1.1 Version Control Systems, VCS. Role, the foundational component, where all code lives and from which all pipelines are triggered. Key players, Git dominant and almost universal, implemented by services like GitHub, GitLab, Bitbucket, Azure repos. Less common now, but historically significant, SVN Perforce. 11.1.2 CI/CD orchestrators, pipeline engines. Role, the brains of your pipeline. These tools define, manage, schedule, and execute the various stages of your CI/CD pipeline. They integrate with VCS to detect changes, trigger builds, run tests, and orchestrate deployments. Key players, Jenkins, an open-source classic, highly extensible with a vast plugin ecosystem, requires self-hosting and maintenance. GitLab CI/CD, built directly into GitLab, offering a seamless, integrated experience from code to deploy. Strong focus on pipelines as code. GitHub Actions, native CI/CD for GitHub repositories using YAML workflows, popular for open source and personal projects, growing in enterprise adoption. Circle CI, a popular cloud-native CI/CD service known for its speed and ease of use. Travis CI, another widely used cloud-native CI/CD service, often popular for open-source projects. Azure DevOps Pipelines, Microsoft's comprehensive suite offering CI/CD for various platforms, tightly integrated with Azure services. Bamboo, Atlassian's CI/CD server, often integrated with Jira and Bitbucket. Trend, shift towards cloud-native, managed services, and pipelines as code. Defining your pipeline in version-controlled config files, typically YAML, for better versioning, collaboration, and auditability. 11.1.3 Build automation tools. Role, executed within the pipeline to compile source code, resolve dependencies, and package applications. Key players: Maven, Gradle, Java; NPM, Yarn, Webpack, JavaScript; MS-Build, .NET CLI, Netcore; CMake, C++; Python SetupPy, Go Build. 11.1.4 Automated testing frameworks and tools. Role, for writing and executing automated tests at various levels: unit, integration, E2E. Key players: JUnit, TestNG, Java; Jest, Mocha, Cypress, Playwright, Selenium, JavaScript, Web; NUnit, XUnitNet; PyTest, Python; Postman, API testing. Specialized tools: load testing, JMeter, K6; security scanning, SonarQube, OWASP, Zap, checkmarks; accessibility, Axe, Lighthouse. 11.1.5 Artifact repositories. Role, securely store and manage binary artifacts. Compiled code, Docker images, packages, produced by the CI pipeline, making them immutable and available for deployment. Key players: JFrog Artifactory, Sonatype Nexus. Cloud providers also offer their own registries for specific artifact types, e.g., Docker Hub, AWS ECR, Google Container Registry, Azure Container Registry. 11.1.6 Infrastructure as Code, ISC tools. Role, automate the provisioning and management of infrastructure, servers, networks, databases, containers, through code, ensuring consistency and reproducibility across environments. Key players: Terraform, Agnostic, AWS CloudFormation, Azure Resource Manager, Google Cloud Deployment Manager. 11.1.7 Configuration management tools. Role, automate the configuration of servers, operating systems, and applications. Key players: Ansible, Chef, Puppet, SaltStack, often used in conjunction with ISC for complete environment setup. 11.1.8 Deployment automation tools. Role, directly deploy applications to various environments, often integrating with ISC and configuration management. Key players: Spinnaker multi-cloud CD platform, Kubernetes container orchestration for deployment and scaling, Helm Kubernetes package manager, cloud-native deployment services, AWS Code Deploy, Azure App Service. 11.1.9 Monitoring and observability tools. Role, collect, analyze, and visualize metrics, logs, and traces from applications and infrastructure to provide insights into their health and performance. Key players: Prometheus, Grafana open source, Datadog, New Relic, AppDynamics commercial APM suites, Splunk, Elasticstack, Elk, Elasticsearch, Logstash, Kibana, logging and analytics. 11.2 Emerging trends transforming CI/CD. The landscape is constantly evolving. Here are some key trends. GitOps extends infrastructure as code to operations as code. It's an operational framework that takes DevOps best practices like version control, collaboration, CI/CD, and applies them to infrastructure automation. The desired state of the entire system, application, infrastructure is declared in Git, and automated processes ensure the live system matches this declared state. AI, ML in CI/CD. Beyond just testing, AI and machine learning are beginning to enhance various aspects: predictive analytics, predicting build failures or performance bottlenecks before they happen; smart test selection, recommending which tests to run based on code changes to optimize pipeline speed; automated incident response, using AI to analyze monitoring data and suggest or even execute automated remediation; chaos engineering. Popularized by Netflix, this practice involves intentionally injecting failures into a system to test its resilience in production. CI/CD pipelines can be extended to automate the execution of chaos experiments. DevSecOps, integrating security practices and tools throughout the entire CI/CD pipeline, shift security left. This includes automated security scanning, SAST, DAST, dependency vulnerability checks, and security policy enforcement at every stage. Serverless and FAS, functions as a service, deploying individual functions instead of entire applications. This changes how build and deployment pipelines are structured, often simplifying packaging and deployment, but introducing new challenges in monitoring and local testing. Supply chain security. With increasing reliance on open-source components and third-party libraries, securing the software supply chain, e.g., verifying component integrity, patching known vulnerabilities, is becoming a paramount concern within CI/CD. Green DevOps/sustainable software development. Growing awareness of the environmental impact of software and computing. Aims to optimize resource usage in CI/CD pipelines and production environments to reduce energy consumption and carbon footprint. 11.3. Advanced practices for mature CI/CD adoption. Beyond the core principles, truly mature CI/CD implementations often embrace these advanced practices. Test data management, TDM, the ability to provision, mask, and manage realistic, consistent, and up-to-date test data automatically for various testing environments. Poor test data is a common bottleneck. Secrets management, securely managing sensitive information, API keys, passwords, database credentials that applications need in production. Tools like HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault are integrated into the pipeline to securely inject secrets at runtime. Experimentation platforms, tools and practices that allow for advanced release strategies like A/B testing, multivariate testing, and controlled rollouts, often built on top of feature flagging capabilities. Cost optimization in pipelines, monitoring the resource consumption of CI/CD agents and builds to optimize cloud costs and build times. Self-service pipelines, empowering development teams to easily create and manage their own CI/CD pipelines using standardized templates and modular components, reducing reliance on a centralized ops team for every pipeline change. Platform engineering, building and maintaining internal developer platforms that provide self-service capabilities and abstractions over underlying infrastructure and tooling, making it easier for feature teams to deliver software. Navigating this continuously evolving technical landscape requires a commitment to continuous learning. No single tool is a magic bullet, and the ideal toolbox will vary based on your organization's specific needs, existing technology stack, and cloud strategy. The key is to select tools that align with CI/CD principles, foster collaboration, and automate manual processes, ultimately supporting your team's ability to deliver value efficiently and reliably. Chapter summary: the CI/CD landscape is vast and dynamic, populated by various specialized tools that orchestrate, build, test, secure, deploy, and monitor software. Key categories include version control systems, dominated by Git, CI/CD orchestrators, like Jenkins, GitLab CI/CD, GitHub Actions, various build and test automation tools, artifact repositories, and infrastructure as code and configuration management tools. These are complemented by robust monitoring and observability suites. Beyond specific tools, several trends are shaping the future of CI/CD, including GitOps, the integration of AI, ML, chaos engineering, DevSecOps, serverless deployment, supply chain security, and green DevOps. Mature CI/CD adoption also leverages advanced practices like comprehensive test data management, secure secrets management, experimentation platforms, and the development of self-service pipelines and platform engineering. Navigating this landscape effectively requires continuous learning and selecting tools that align with core CI/CD principles and foster collaborative, automated delivery. 12. Your CI/CD journey. Getting started and evolving. You've embarked on a comprehensive journey through the world of continuous integration and delivery. We've dismantled the maze of traditional software delivery, explored the foundational philosophies of Agile and DevOps, delved into the mechanics of CI, version control, automated testing, and the full CD pipeline, culminating in the advanced leap to continuous deployment. We've also touched upon the critical human element and navigated the bustling landscape of tools and emerging trends. Now, you might be asking, where do I begin? How do I apply this to my team, my organization? The answer is simple yet profound. Start small, learn continuously, and focus on value. CI/CD is not a destination, it's a journey of continuous improvement. 12.1 Getting started, taking the first steps. Implementing CI/CD doesn't require an all-at-once, big bang approach. Gradual, iterative adoption is far more effective and sustainable. Assess your current state, the why revisited. Identify pain points. What are your biggest frustrations with current software delivery? Long release cycles, too many manual errors, integration headaches, slow feedback. Identify the specific problems CI/CD is intended to solve for your team. Baseline metrics. Before you change anything, establish baseline metrics. How long does it take for a code change to reach production? How often do you release? What's your change failure rate? These numbers will help you demonstrate progress later. Secure leadership buy-in and find champions. Educate, present the why to your leadership. Frame CI/CD not just as a technical initiative, but as a business enabler that leads to faster time to market, higher quality, and reduced risk. Recruit enthusiasts. Find individuals or small teams who are excited about CI/CD. These champions will be your early adopters and internal evangelists. Start small, the pilot project approach. Choose wisely. Select a relatively small, non-critical project or a less complex part of a larger application. Avoid mission-critical systems for your first attempt. Define success metrics. What defines success for this pilot? Perhaps it's automating the build, then adding basic unit tests, then achieving daily successful CI builds. Implement core CI practices first, focus on automation and feedback. Version control mastery. Ensure your team is proficient with your VCS, ideally Git. Enforce frequent, small commits. Automate your build, get a reliable, automated build process working. Implement unit tests. This is crucial. Ensure tests are executed automatically as part of the build, and the build fails if tests fail. Follow the fail fast principle. Make build status visible. A monitor displaying build status, green-red, provides constant feedback and fosters transparency. Fix broken builds immediately. Instill the discipline. The team must prioritize fixing the build. Expand gradually to continuous delivery. Automate deployments to dev/test environments. Once builds are stable, automate the deployment of your artifacts to your non-production environments. Add more automated tests. Introduce integration tests, and then a select few, high-value E2E tests. Standardize environments, ISE. Work towards making your development, testing, and ultimately, production environments as similar as possible using infrastructure as code. Manual production gate. For continuous delivery, retain the manual, go-no-go decision for production deployment, but ensure the mechanism of deployment is automated. Invest in culture and training, cross-functional teams. Encourage developers and operations to work together and share knowledge. Skill development. Provide training for new tools and practices, especially around test automation and pipeline definition. Blameless postmortems. When failures occur, focus on learning and improving, not blaming. This is a critical cultural shift. 12.2 Evolving your CI/CD maturity. Once you have a functional CI/CD pipeline, the journey shifts to continuous refinement and reaching higher levels of maturity. Move towards trunk-based development. Reduce the duration of feature branches, aiming for faster, more frequent integrations into the main branch. Deepen automated test coverage. Continuously improve your test suite, adding performance, security, and accessibility tests. Focus on making tests reliable and fast. Embrace observability. Beyond basic monitoring, instrument your applications and infrastructure to gain deep insights into their behavior in production. This feeds the feedback loop. Implement advanced deployment strategies. Explore blue-green, canary, and rolling deployments to minimize deployment risk and downtime. Experiment with continuous deployment. For suitable applications, cautiously automate the final step to production, provided you have absolute confidence in your automated tests and monitoring. Build self-service capabilities. Empower development teams to manage their own pipelines, adhering to organizational standards but removing bottlenecks. This might involve creating internal platforms or standardized pipeline templates. Refine your feedback loops. Ensure that learnings from production bugs, performance bottlenecks, user behavior consistently feed back into the planning and development cycles. Contribute to inner source/platform engineering. Encourage wider collaboration by treating internal tooling and common components as open source projects, inner source. Fostering shared ownership and accelerating innovation. 12.3 What to watch out for common pitfalls. Even with the best intentions, organizations can stumble on their CI/CD journey. Be aware of these common pitfalls. Treating CI/CD as a purely technical initiative. It's not. Without cultural change, collaboration, and management buy-in, even the best tools will fail to deliver promised results. Lack of automated testing. A pipeline without comprehensive, reliable tests is like an automated car manufacturing line that just assembles parts, never checking if the engine actually works. It's an illusion of progress. Ignoring a broken build. Letting pipelines stay red undermines trust and quality. It's a sign of a decaying CI/CD practice. Over-engineering tooling. Don't get caught in tooling mania. Start simple with proven solutions and only introduce complexity when truly necessary to solve a specific problem. Neglecting legacy systems. Some older systems may be difficult to integrate. Don't ignore them, but also don't let them halt your progress on new, more agile systems. Address them strategically. Lack of training and support. Expecting teams to adopt new complex tools and practices without sufficient training, mentorship, and support will lead to frustration and resistance. Focusing on speed over quality. A pipeline that is fast but frequently delivers buggy software is not effective. Quality must be built in from the start. 12.4 Conclusion. The mindset of continuous improvement. The world of software development is constantly evolving. In this dynamic landscape, the ability to build, test, and deliver software continuously and reliably is no longer a luxury, but a fundamental requirement for survival and success. Continuous integration and delivery provide the methodology and the tools to achieve this. But remember, the true power of CI/CD lies not just in its technical capabilities, but in its ability to foster a culture of collaboration, transparency, and relentless improvement. It's about building trust. Trust in your code, trust in your processes, and trust in your team. Your CI/CD journey is a marathon, not a sprint. Embrace the challenges, celebrate the successes, and always remember that the goal is not merely to ship code faster, but to deliver better value, more reliably, and with greater joy for everyone involved. The Agile Pipeline awaits its next iteration.